So this is page 94, question 9, which it was one of the ones I recommended you looked at after Wednesday's lesson. And I said I'd start today by talking about it. So we have a classic binomial setup here. No mention of the binomial, but it is, 10 residents, fixed number of trials, 30% listen to the radio, fixed probability. So when it says suggest a suitable distribution for x, you would say this, and you would say we have assumed that we are always going to ask 10 people. The probability stays the same. The asking people is independent, and it's just about putting those 4 criteria for using the binomial into context. It's a 2-mark question, so they probably expect quite a bit of context. But that's how you would answer that. The probability that at least half of these residents listen to local radio. So we are going to binomial, and we're going to enter our parameters. So we've got number of trials is 10, and the probability of success is 0.3. And we've got to think hard here about what at least half means. So we can have anything between 0 and 10. 5 would be half of them. At least half means that, doesn't it? So we had lower of 5, upper of 10. Lower of 5, upper of 10. Now remember, what the calculator is doing is it is calculating separately the probability of 5 successes, 6 successes, 7 successes, 8 successes, 9 successes, and 10 successes, and it is adding them up for you. And that's 0.1503 when we round it. So that was 0.1503 when it is rounded. Now, we're then asked one of these reverse questions. Now, so what we are being asked is, what is the first value of x which gives you a probability of less than 0.01? But the question is this one of these ones down at the left end or at the right end? So you've got to look at what they're asking here. So they want us to find a value of s so that if x is bigger than or equal to that, the probability is 0.01. So we're talking about moving in this direction. Left tail problems, we're moving in that direction. We're asking what about if x is less than or equal to a value? So you can sort of summarize it like this if you want, with these inverse probability questions, inverse binomial questions. If they're asking for a value of s such that when x is less than or equal to it, we're talking about a left tail problem. If we're talking about x being greater than or equal to a particular value, then we're talking about a right tail problem. So this is a right tail problem. So I'm hoping perhaps you paused at that point and made a note of that. This is why I do like pre-recorded videos, and we're also on take 3 for this one. So if it was a live lesson, I would have probably confused you by now. So I know already that the trouble is that s looks a bit like 5, but I know when I did 5 or more, I got that probability there, which is still considerably bigger than that probability there. So I knew that for 5 or more, it was that. And I want to know the first value that drops below that. How did I know the peak was at 3, by the way? Remember, it's that tells you where the peak is. And this is just a sketch, no accuracy required at all. So I know I'm looking for a value of s that's bigger than 5, and that means I've only got a few values to try. 6, 7, 8, 9, 10. So if you haven't done this question, pause and try those values. And if you did do the question, you can skip this next pause, because I'm going to pause and have a go myself. We can all get together when we've had a go. So when I did 6 to 10, because we're asking here not greater than, but greater than or equal to. So when is it greater than or equal to 6? That's lower 6, upper 10. I got that. That's still bigger than 0.01. When I did 7 to 10, I got that, which is still bigger than 0.01. When I did 8 to 10, I got a number that was much smaller than 0.01. The good news is we don't need to interpolate here though, because x is discrete. It can either be 7 or it can be 8. So what number here gives you the first probability less than 0.01? The answer was 8. The answer was 8. Okay, here's the next problem. No context, so we haven't got to worry about defining our parameters. They're defined for us. We haven't got to state the assumptions. We're doing something 40 times, and the probability of success is 0.45. Remember, you get a pretty symmetrical distribution if you're close to 0.5. 0.5 would give you a perfectly symmetrical distribution. I also know roughly where the peak will be. That times that gives me 18. So 18 is the peak. Pretty much halfway, because the lowest is going to be 0 and the highest is going to be 40. And remember what these lines I'm drawing, actually it's bars, isn't it? You know, you've got 41 bars from 0 up to 40, but this is just the general shape. Now, is this a left tail or a right tail problem? We want to know the value of C somewhere along here. So the probability of x being less than that is something close to 0.6. So we know that because that's a less than problem, we're dealing with a left tail problem. However, this is a left tail problem with a difference, because that's quite big, isn't it? So far we've had questions with probabilities like 0.01 or 0.05. 0.6 is quite big. That's more than half of the probabilities. Remember, all the probabilities will add up to 1. Now, if it was a perfectly symmetrical distribution, I know the probability of 0 to 18 would be a half. It's not symmetrical, so 0 to 18 won't be exactly a half, but I'm pretty sure that this value is going to be somewhere around here. It's going to be somewhere around halfway. This is roughly half of the total probability. So I'm going to try starting at, I'll do 17, I'll do 18, I'll do 19, I'll see what happens. Maybe I need to do a few more, I don't know. It's less than or equal to 17, so I know for this one it's going to be lower 0, upper 17. But I have a feeling that the value of C is somewhere around there. Let's see if we can find it. Pause, find those for me. Okay, so 0 to 17 was less than 0.6. Remember, I want the last value, the maximum value that gives you a probability of less than 0.6. 0 to 18 was less than 0.6. 0 to 19 was bigger than 0.6. Remember, we're not having to interpolate because we can only have these whole number values. So what is the biggest value that gives you a probability of less than 0.6? 18. So C was actually 18. That was the answer to that question. Okay, here's another one in context. So just pause and see if you can state the parameters, and then can you work out what this question is asking, and most importantly, left tail or right tail. Have a think. Okay, so hopefully you got your parameters. If you are guessing on a multiple choice test with 4 options, your probability of success is 1 in 4, 0.25. So we want the probability of passing by guessing to be 10% or less. So I'm in the middle of writing my inverse statement here, and I know the bit here is going to be less than 0.1. But what goes in the bracket? Because it's the bracket that decides whether this is a left tail or a right tail problem. Let's say the pass mark is 15. Do you pass if you get 15 or less, or 15 or more? Well, you pass for 15 or more, don't we? So we want to find the pass mark so that the probability of getting that or greater than that is less than 0.1. So this is a left tail problem. Okay, So now we need to find the value of m. So you're going to try different values here, getting steadily bigger, and you want the first one that drops below 0.01. So if you set the pass mark at, sorry, firstly, my diagram's dreadfully wrong, isn't it? I mean, I know this probability is quite low, so the peak is going to come early and then you've got a long tail. But yeah, when I started with values of sort of like 20 to 30, I was getting tiny, tiny probabilities, so I had to go all the way down to 10 to get something that was reasonable. So if you set the pass mark at 10, you have almost a 20% chance of passing by guessing. We want the first mark that gives you a probability of less than 0.1. 11, you've still got more than 10% chance of passing. So if you set the pass mark at 12, your chance of passing by guessing is down at 5%. So the first value of a pass mark that gives you less than 10% is 12. Now I noticed it said 10% or less. I guess there is a chance that you could get a probability that was bang on 10%, but no, this is more than 10%, this is less than 10%, so the pass mark needed to be 12. So if you look on OneNote, you'll notice I've created a new folder called Regular Submissions. That's separate from the weekly homeworks. And this is to try and build up that accountability for those of you who are struggling to keep up. So I would like you to have a go at this question. I'd like to have a go at this question today. And I'd like you to post a photo of your answer on OneNote today. Okay, I'm going to start doing this regularly. And some of you I know are keeping up with the videos and you are doing them on your own timetable because that suits you best. That's fine as long as you are not falling behind. I don't need you to do it at the exact time of the lesson, but some of you I know are struggling, so I'm expecting those of you, and you know who you are, to be doing this lesson when you would have this lesson in school, and so I expect to see your answer for that pop into OneNote shortly after the end of when the lesson would be. Okay, so have a go at that question. Right, let's move on to something else relating to the binomial though. Okay, so here is another binomial question in context. So I'll give you a second just to read it. So we are creating batches of 12 plates, and there is a 10% chance that plates have minor faults. So we are asked to count the number of faulty plates in a batch and model that with a value x. So state the appropriate distribution with which to model x. I realise I haven't been very clear about how to answer these questions. I've just said, oh, you state the assumptions in context. So I'm going to be really clear about this one. So I think I would write, you're perfectly okay saying this, but I wonder if I might actually, me being a belt and braces fan, I might write x can be modelled. Modelled got two L's? Modelled. I apologise to the English students, hopefully you'll be able to tell me, as a binomial distribution. I'd write that first, and then I'd do my x and 12, 0.1. That's what I'd do. And then I'd go on to talk about the assumptions, okay? So I'd say, right, the plates are always stored in batches of 12. It is always clear whether they are seconds or not. The probability of a plate being faulty is always 10%. And if one plate is broken in a box, it is no more likely that another plate is broken. Now, I did say I would come up with an example of the difference between these two, and I think this suggests an example, because I think the probability of success, in this case, is the probability that it's faulty, so actually success is the wrong word. That's to do with manufacturing, isn't it? But if you're putting them in a box, how are they going to get damaged in the box? Well, they could get dropped. So if one breaks in the box, perhaps others are more likely to break. So the whole independence thing is more about how they're put in the box. Are they packed in nicely? So I would say the probability of them being faulty is always 10%. And if one is broken in a box, it is no more likely that another will be broken in a box. That's what the independence is about. So that's how I would answer that question and earn those 4 marks. Quite a lot of marks for that. This is an old spec question actually, so I think there were more marks in total. Okay, so now we can forget all about those assumptions. So go on, calculator, just do those 2 for me. Pause and have a go. Okay, so I had lower and upper of 3, having entered n and or number of trials and p. Lower and upper of 3, and then this one is lower of 1, upper of 12. So this is basically the probability that you've got any faults, all right? So this is probability that you've got 1 or more faults. The probability you've got at least 1 fault, or they refer to them as seconds, don't they? So like a second is a faulty plate. Okay. Now, any of you fans of those Russian dolls? Those are those dolls where you open one doll and inside the doll there's an identical doll but a little bit smaller. Well, this is a question which is like that, because what we now have is another binomial distribution. We take 4 batches, and now all we're doing is we're checking whether or not they have at least 1 fault in them. So we now have a binomial where we're checking 4 batches. What's the probability of success? Success is that we find at least 1 fault. If only we had a way of working out what the probability of, in a batch of 12, there being at least 1 fault. Oh, hang on a minute. Yeah, we've just worked it out. That probability we've just calculated is the probability of success in this question. We've got a binomial within a binomial. So here we're taking 4 of these batches, and we're not worried about how many faults, we're just worried about whether they have any faults or not. And the probability in a batch of 12 of finding at least 1 fault, 1 second, we just calculated it. So we want to know what's the probability that in our batch of 4 we have less than 3 batches with 1 fault. Not less than or equal to 3, less than 3. Go on, see if you can bring it home. Okay, so I know some of you are saying that's a rounded value. Yeah, you're right. Unfortunately, there's no way on the calculator to sort of paste the exact value in there. So 4 decimal places is fine. So number of trials is 4, and less than 3 is 0, 1, or 2. So lower 0, upper 2, and that is the answer. So this binomial within a binomial is, it can be hard to spot, although if you've got a question where you go from having one number, in this case batches of 12, to another number, batches of 4, but it's the same sort of thing, it's a bit of a giveaway. And there's only one question in the textbook on it, so maybe I'm being foolish to expose you to, I don't know, but have a go at that one. So that's not a sub-question for submission, that's one from the textbook that I'm hoping you'll be able to find the answer for. But if you can't, then don't forget that, well, I say don't forget, I'm not sure I mentioned it to 12E, but on Friday, I'm just going to set up a 45-minute Teams meeting. You'll all be invited, but you don't have to go unless you've got a question. So it might be that a few of you pop up and ask a question about page 97, question 15. I would commend it to you. Right, I know, as we're often with topics, we start off and the binomial probability distribution is quite easy and it's quite nice and we're using our calculator, and we've sort of slogged our way through some really tricky problems, haven't we, over the last couple of lessons, and I can't avoid that. I'd much rather be doing it face to face. But But you've got one question to submit, which is an inverse binomial question. You'll find that in OneNote in the regular submission folder. And you've got an independent study question to try as well, which is one of these binomials within a binomial. And I will see you tomorrow.